I figured I'll add a little bit of information here on the Pacific Meridional mode and the South Pacific Meridional mode. Just because we mentioned it in the previous podcast on the connection of the Pacific Meridional mode to the heat waves over the Indian Ocean, and that particular paper by Vittal Hari tends to kind of be not so detailed on the connection between Pacific Meridional mode and El Nino, and whether El Nino is needed to go to the Indian Ocean, or can we directly go from the Pacific Meridional mode to the Indian heat waves. So just look at these for what they are worth, and then read the papers and try to make up your own mind. I suspect there will be more papers on the heat waves and the Pacific connections. Anyways, the argument there was that the El Niños don't explain the heat waves, but the Pacific Meridional modes do. But there are also papers by Ping Chang and others arguing that majority of the El Niños are explained by the Pacific Meridional mode triggering. So this is also touching a little on how the PMM, or the Pacific Meridional mode, can trigger an El Nino. And this is a paper by Dylan Amaya. It's a review paper about Pacific Meridional mode and El Nino. So he's starting with showing the maximum covariance analysis process method, which takes two variables and extracts the most covarying patterns and provides the time series that go with those combined patterns, kind of like combined EOFs, except combined EOF gives you one time series for the two variables involved. But these are essentially statistical ways of doing things. So this is looking at SST and 10-meter wind anomalies from 1979 to 2018, and you can see here that this is calculated for the region 21 south to 32 north, 175 east to 95 west from 1979 to 2018. For all the XY maps, shading is the SSTA and arrows are 10-meter wind anomalies. So here we are looking at SSTAs and 10-meter wind anomalies regressed on normalized SST expansion coefficients, which are shown here. So each pattern comes with expansion coefficient. You multiply the two together to get the actual anomaly, just like in EOFs. Black contours are sea level pressure anomalies regressed on 2-month lagged SST expansion coefficients, that is SSP's SLP, sea level pressure leads by 2 months. So this gives you the so-called North Pacific oscillation, this north-south pressure contrast or pressure gradient, and the idea is that random variations or internal variability in the North Pacific oscillation can trigger wind anomalies over the southern edge of this part, which is our Pacific Meridional mode that we are interested in. And if you remember, the mean winds are northeast trades here, so if you have wind anomalies going the other way, in the positive mode you weaken the trade winds and reduce the latent heat flux, and you warm the sea surface temperatures, and then you have interaction with the ITCZ and the precipitation. There are also asymmetric forcings across the equator where the winds cross and run again into the northeast trade winds, and that results in what is called the wind evaporation SST feedbacks. And because of the Coriolis here, there is asymmetry across the equator as the winds cross, so you get cool SSTs here. Generally these are enhancing the trade winds and creating enhanced latent heat losses and cooling, whereas here you get the warming. So you have this nice patterns, but the main point of this is the so-called seasonal footprinting mechanism that was originally proposed by Dan Wymont and collaborators from University of Washington, which argued that once there is a stochastic forcing that initiates the Pacific Meridional mode pattern in the winter months, there is a persistence of the SST wind feedbacks, and that then tends to generate wind anomalies on the equator and initiate summer deep convection responses, and also wind stress curl anomalies, and the ocean can also get involved, and so on and so forth. Nonetheless, looking here at the expansion coefficient for the SSTs and winds and their seasonalities of monthly variance, you can see that there is a phase lag between wind maximum covariance or expansion coefficient and the SSTs. So the winds lead the SSTs here. So black contours are SLP anomalies, which we already said, and SST and wind ECs describe time variability of the maximum covariance analysis 1. First number in the title is squared covariance fraction, which is 72% for the MCA1. Second number is in the title is correlation of the two expansion coefficients, which is remarkably high at 0.86. The main point made with by Dylan and others is that there is a life cycle associated with the Pacific Meridional mode. So you can see that December, January, February, there is the sea level pressure anomaly that generates the original footprinting, and then that extends into the tropics and generates wind anomalies, so persists into March, April, May. June, July, August is when you get the ITCZ, which is obviously at its northernmost position in the summer months, and then that is influenced by the meridional mode induced wind anomalies, and you get persistence into September, November as well. So you get this life cycle, and the main point to remember is that even though the North Pacific Oscillation forcing may be random or stochastic, there is a way that the Pacific Meridional mode can take that forcing and generate a systematic mode that evolves through the season and has a life cycle. These are basically the same thing: January to March latent heat flux regression and April to June latent heat flux regression. So January to March average SSTAs in these black contours and 10 meter winds in the vectors and latent heat flux anomalies in shading basically tell you about the enhanced heat loss or reduced heat loss from the ocean, and how they are producing this WES feedback, or the wind evaporation SST feedbacks, which persists the seasonal footprinting mechanism from the random forcing into this life cycle. So this is same as this, but for April to June averaged variables. In order to be consistent, figure 1 to G, and so ENSO not linearly removed from data prior to taking regressions. SST data is from had ISST, and atmospheric variables from reanalysis era 5. So I'm not going into the details, but you can follow up on the climatological winds and the anomalies and the corresponding enhanced and reduced latent heat losses, which are very important in terms of persisting the initial forcing in the meridional mode and producing the life cycle. So here they are trying to look also at the precipitation response and the ITCZ shift, and the shift that results in heating anomalies and produces the so-called gill response. So if you have elevated heating in the atmosphere, you get surface response in terms of waves and convergence, upper level divergence, and so on, which is known as the classical gill response. When you shift it off the equator, you get monsoonal type circulations feeding into the heating as well. So joint EOF 1 of August to October average SSTAs and precipitation anomalies in observations and the mean of a 10-member ensemble of the boundary forced atmospheric model simulations M atmosphere. And basically the idea is that to show that even if you give only the North Pacific SST anomalies to an atmosphere, it can produce the seasonal footprinting mechanism and the deep tropical wind anomalies, which means the Pacific Meridional mode does have a tropical footprinting, the so-called seasonal footprinting, and there is the associated rainfall anomalies in these green arrows, and observations and this so-called AMIP run, or the forced atmospheric run, have a remarkably high correlation at 0.97, but the explained variances are different in the observations at 31% and in the model at 47%, which happens. The trick here is, of course, that when you use SSTs to force the atmospheric model and argue that just given the SSTs in the North Pacific it can reproduce the tropical response and hence it is related, is that the SSTs themselves are produced in a coupled system which you are taking from observation. So in some sense it's not a very clean process, but nonetheless they do give you some information on how the processes are occurring. This is the argument in the paper on how the seasonal footprinting and Pacific Meridional mode can actually generate El Nino. So as I said, the heatwave paper argues that the El Nino forcing is, and the El Nino forcing by the Pacific Meridional mode and the El Nino forcing of the heat waves are not critical, that they can go directly from the Pacific mode to Pacific Meridional mode to the heat waves, but you should keep this in mind. So schematic illustration of the primary physical pathways linking the North Pacific Meridional mode to ENSO. They include, usually when we said Pacific Meridional mode we only meant the northern part, but since the South Pacific Meridional mode was also discovered, this has now become NPMM, and if you remember the previous heatwave paper they only referred to it as PMM, or the Pacific Meridional mode. So this includes wind evaporation, SST feedback, the WES feedback. So the wind anomalies are weakening the trade winds and producing latent heat loss drop and creating warm SST anomalies, and summer deep convection response, or the SDC response, during July to October. So sorry, that's during the boreal spring in the solid black arrows. Trade wind charging, TWC, of the equatorial subsurface heat content by the NPMM related surface wind stress curl anomalies in boreal winter and early spring. So that's the wind stress curl being shown here, which can lift or suppress the thermocline and create sphered transport, convergence or divergence, which is the trade wind charging, which assists with the ENSO recharge discharge process, for example. And thirdly, the reflection of the NPMM forced ocean Rossby waves off the western boundary in boreal summer in red dashed arrows, and producing Kelvin waves with the red dashed arrows. So reflected Rossby waves coming in as Kelvin waves, which is a typical process for forcing El Nino or initiating an El Nino. Fourth, gill type summer deep convection response, which is going to reinforce the seasonal footprinting, and this goes from boreal summer into fall, known as the summer deep convection response, clouds and solid gray arrow lines. So each mechanism provides an opportunity for the North Pacific Ocean atmosphere anomalies to influence ENSO development, either by altering the off-equatorial ocean circulation in pathways 2 and 3, so 2 and 3, wave reflection and wind stress curl response, or by generating zonal wind stress anomalies along the equator, as in pathways 1 and 4. So 4 is producing the winds, and 1 is is here in the spring west feedback. Shading in the XY plane is the same as in 1A. Shading in the XZ plane is regression of observed surface potential temperature anomalies averaged over 5 south, 5 north on SSTA EC, depicted in figure 1b, so expansion coefficients. Essentially, this is the recharge discharge mechanism, which has the leading meridional tilt first and then the zonal tilt, which is the onset of the El Nino, and it has its own life cycle. Just to conclude, this is a separate paper which shows that there is a South Pacific convergence, South Pacific meridional mode, which looks exactly the same, and the same processes occur. So you see here the wind anomalies and the west feedback. Here, of course, you have the southeasterly winds being weakened by these meridional mode wind anomalies, reducing latent heat loss, warming SSTs, producing the other signal, and the forcing presumably is similar with random forcing from sea level pressure anomalies, and they do lack correlation. So here 10-meter wind anomalies and sea level pressure anomalies in contours and shading with monthly SST anomalies are shown, but you can see the similarity to the North Pacific meridional mode. Contour intervals are given here as 0.4 HPA and 5 watts per meter squared for latent heat loss. Reference wind vector is 0.7 meter per second. Positive and negative values are represented by solid and dashed contours. Zero contour is omitted. Positive and negative latent heat flux anomalies indicate anomalous heat flux into or out of the ocean, so you have to always be careful of the convection. Stippled areas indicate significance of the SSTA at the 95% level according to a two-tailed student's t-test. Always good to do statistical significance test. And only significant wind vectors are shown. Here lack correlations between expansion coefficient 1 for wind and expansion coefficient 1 for SST are shown, and you can see that there is a lead lag relation. Maximum correlation happens at winds leading by about a month, which is what happened in the northern hemisphere as well. Okay, so negative lags indicate that wind index leads the SST index. This is the seasonality of EC1 wind and EC1 SST. Again, winds lead the SST as in the northern hemisphere, and these are the long time series. So this is the overall correlations, and these are the time series associated with that. There are even these regime shift kind of behaviors here that occurred around the mid 1970s and maybe also in the 2000s, but let's not get into that. So there are arguments that the South Pacific and North Pacific meridional modes together determine the Pacific decadal variability, which we will not get into. So maybe this is good to leave it here together with the heat wave paper so that you have a good sense of what the meridional modes are, how they are related to El Nino, and how challenging it is to separate the El Nino impact on things like the pre-monsoon heat waves and the monsoon itself, and the relations to meridional modes and how they may trigger El Nino, or whether they provide decadal variability and background so-called ENSO variability, where the ENSO duration, frequency, and intensity themselves are shown to vary at those time scales, which is also related to Pacific decadal variability, which is another mode of variability that's not the same as the meridional mode. Okay, so I don't want to confuse you, but we have discussions on other modes of variability elsewhere, and you can look them up. Okay.